we see the unit of voltage everywhere in daily life. 1.5 volts in a simple battery, 5 volts in a smartphone charger, 230 volts in a wall outlet, and over 400,000 volts on massive overhead power lines. Even inside a microchip, a tiny 0.7 volts threshold is what allows a transistor to operate. Yet, despite how common it is, voltage remains one of the most misunderstood concepts in physics. Ask most people and they will tell you that voltage is the amount of electricity, a fluid moving inside wires, or the total power stored in the system. In reality, voltage is none of these things. It is not a physical material and it is definitely not a measure of electric current. Voltage is a property of the electric field itself, an invisible difference in potential between two specific locations in space. Welcome to VastVoltage. Let's visualize the invisible. To understand voltage, let's look at how height and depth work in the physical world. Altitude is measured from a universal reference point, sea level, defined as 0 meters. Electrostatics works in a similar way, using a vertical landscape of electric potential. Initially, without any external force, all matter sits balanced and neutral. There is no charge separation and no voltage. Now imagine a non-electric force grabbing a negative electron from a neutral atom at the top level and forcing it straight down into a deep trench below. By stripping away that electron, the atom left behind at the top becomes a positive ion, forming a mountain peak of positive potential labeled V1. Down in the deep trench labeled V2, we now have a surplus of a negative electron. Between them sits sea level, or 0 volts, our neutral ground reference. This vertical separation creates an electric field pointing straight down. Because opposite charges attract, the positive ion at the top pulls the electron back up. The electron experiences a strong upward electrostatic force. It acts like a helium balloon forced down in the air, desperately wanting to shoot straight back up to reunite with the positive ion. Voltage is simply the vertical height gap of this landscape. It is the potential difference between the peak and the trench. Now let's look at the physics of how that electron was forced down in the first place. To submerge a helium balloon deep underwater against water pressure, you must perform mechanical work. The exact same rule governs electricity. To separate charges and create voltage, an external force must move an electron from the top level and force it down into the negative trench against the electrostatic force. In real devices, this external force comes from non-electric energy, chemical reactions inside a battery, mechanical motion in a generator, or photons hitting a solar cell. All of them act like a non-electric elevator, forcing electrons down into the deep trench where they don't want to be. As this elevator pushes the electron straight down, it performs work, expanding an invisible electrical spring. This work is not lost. It is stored in the system as electrostatic potential energy. The greater the distance, the higher the vertical voltage gap and the more energy each electron holds. This gives us the formal definition of voltage. Voltage is the amount of work required per unit of charge to move a charge between 2 points in an electric field. 1 volt is defined as exactly 1 joule of work used to move 1 coulomb of charge. It measures how much potential energy each single coulomb gains when forced down into the trench or releases when shooting back up to the peak. But what happens if the elevator keeps running? Moving the first electron is easy, but moving the second one requires more work because the first electron is now repelling the second one and the number of attracting positive ions grows. As the elevator forces more charges into the trench, the electrostatic force grows. The mountain gets taller, the trench gets deeper, and the voltage increases. This dynamic growth explains a famous paradox in physics. During winter, walking on a carpet can build up a potential of 10,000 volts on your body. Yet, a car battery operates at only 12 volts. How can 10,000 volts be harmless while 12 volts can hold massive power? The secret lies in the shape of the trench. In engineering, we call this capacitance. Voltage equals the total charge divided by the capacitance of the system. Capacitance is simply the width of your trench. Your physical body has a very low capacitance. It acts like an incredibly narrow tube. To give you real numbers, a human body has a capacitance of only about 100 picofarads. When your shoes transfer just one single microcoulomb of charge, separating it across this narrow tube, the math dictates an instant spike. The total potential difference shoots up to 10,000 volts. It is an extreme electrical gap, but it holds a very small electrical charge. When you touch a metal door handle, you empty that narrow 10,000 volt tube in a fraction of a microsecond. Because the voltage is so high, it ionizes the air, creating a bright flash of light, a sudden zap. But since the total amount of charge was tiny, the overall energy is barely a few millijoules. It is completely harmless. A car battery operates in a completely different way. Unlike a simple capacitor, a battery stores its energy chemically inside a massive wide reservoir. Its internal chemical elevator pumps charges to create a potential difference. But this reaction has a strict physical limit. It can only push against a back pressure of 12 volts. Once the potential difference reaches 12 volts, the system reaches chemical equilibrium. The elevator stops. The voltage doesn't keep growing higher. Instead, the battery holds a massive quantity of chemical energy, storing thousands of coulombs at the exact 12-volt level. Now the stage is set. When a conductive wire connects the trench back to the mountain peak, that stored energy is released. The trapped electrons shoot straight back up through the wire to neutralize the positive ions, doing useful work along the way. When you drop a steel wrench across a car battery, you open the floodgates of a massive 12-volt chemical reservoir. The trench is shallow, but the massive reservoir delivers millions of joules of total energy. The continuous heavy flow of electrons creates brutal heat, easily melting the solid metal. This flow of electrons, whether it is a tiny spark jumping to the air or a massive stream hitting a piece of solid metal, it is what we call electric current. We now understand the invisible pressure, but how exactly does this current move through a conductor? We will decode this mystery. If this video helped you see the world in a new way, make sure to subscribe, like and drop a comment to join our mission. Mastering engineering starts with visualizing the invisible. I am VastVoltage. See you in the next one.